Okay, so based on the formulas we just deduced, the total index of a Cauchy medium is now n equals n0 plus n2 times I. n0 is the linear index we have been familiar with. And n2 times I is the index change due to optical curve effect. Okay? And usually n2 is referred to the Kerr coefficient. Okay. Without proof, the response time of n2 is actually very, very fast, in the order of 1 femtosecond, okay? Which is fast enough to react to the instantaneous electric field fringes, not just the envelope, but also the fringes, okay? So it's too fast that we can assume the Kerr effect is simply instantaneous, okay? You don't have to worry about the finite dynamics 因为它反应速度太快了，快到连 carrier cycle 比 carrier cycle 都快 ，not to mention the envelope. So we can just assume Kerr effect is almost instantaneous. As long as you have some change about your electric field, the index change N2I will immediately show up. Okay. Then I show you some real numbers about the N2 values of typical materials, such that you have some sense about how strong the Kerr effect is. The most used material in making optics is fused silica, right? Just glass. And also disulfide crystal, making disulfide lasers. The corresponding N2 value is in the order of 10 to the minus 16th centimeter square per watt. Okay? The number is pretty small, but we shall see whether the effect is weak or not. And the silicon is a very popular semiconductor material. The N2 value is 2 orders of magnitude stronger than glass, 10 to the minus 14th. Okay? So some research activities involved with using silicon instead of silica as a Kerr medium because of the much stronger N2 value. But compared with new material graphene, the N2 values are pretty small, right? Graphene has 10 to the minus 7th centimeter square per watt. So it has a very, very strong Kerr nonlinearity. And if even you don't use any material, at least your laser beam will propagate through the air, right? And even the air has non-zero nonlinearity. The N2 value is in the order of 10 to the minus 19th centimeter square per watt. So if your laser intensity is strong enough, even the air, you cannot ignore the effect due to the air. Even the air will broaden your spectrum, as we should discuss later. Okay, if your laser intensity is truly strong, that's a phenomena you will see. Okay, then the following question is how strong the Kerr effect could be. We have seen some N2 values of typical materials, but we don't know whether the Kerr effect is strong or weak yet. So let's consider 2 examples. You have 1 milliwatt helium neon laser with 1 millimeter beam diameter, which is very typical. And the corresponding light intensity is about 0.1 watt per centimeter square. Okay? And using the formula we just deduced, index change equals N2 value times I. If I use silica as the material, N2 is about 10 to the minus 16th. and I equals 0.1. So the product is about 10 to the minus 17th. The index change is in the order of 10 to the minus 17th. So you would assume it's not important at all, very small, right? In the second example, let's assume the dielectric breakdown intensity. Okay? It's in the order of 10 to the 9th watt per centimeter square, and the index change is about 10 to the minus 7. It's still very small, right? But does a small index change necessarily correspond to a small Kerr effect? Okay, that is my following question. Whether this index change, okay, 10 to the minus 17th or 10 to the minus 7th, are important or not, and why is that? We have a plane wave formula like this, right? So what is the accumulation phase change? N is replaced by index change. K0 equals 2 pi over lambda, right? Z is replaced by the interaction distance, big L. So that is the phase accumulation. So if this is only 10 to the minus 7th, how about the phase change? It depends on L over lambda, right? Working distance L over wavelength lambda. And the wavelength lambda is usually very short, in the order of 1 micron, right? So if I need a phase change of 2 pi, what is big L over lambda I need? Good. Since lambda is very small, it's 10 to the minus 6 meters, right? 1 micron. So what is big L? 10 meters, okay? Not that large. If you have a spool of fiber, you can easily accumulate very strong nonlinear phase shift, okay? So usually the Kerr effect is extremely important in fiber optics. But if you have only solid-state crystals inside your laser system, it could be not that important unless your light intensity I, here I only assume breakdown intensity. But if you have femtosecond lasers, you know your light intensity I can be much, much stronger. Then in that case, even solid-state crystals could introduce very significant Kerr effect. Okay, so be careful. Do not just watch the index change, but the phase accumulation. Okay, if you have 2 pi phase accumulation, it's already very strong Kerr effect. Then we are ready to talk about the temporal phase modulation via Kerr effect. Oh, okay, but before we move on, let's go back to the N2 values of the 4 materials I show you. Okay. As I mentioned, graphene is very spatial. The N2 value is like 9 orders of magnitude stronger than glass. So intuitively, you would like to take advantage of this big N2 value by using graphene in your devices, right? But what is the problem of using graphene? Last time we mentioned that graphene is easy to be damaged. And here, as I just showed you, big L over lambda is important. What is the big L you can have by using graphene? It's pretty hopeless, right? single layer atom, the working distance is extremely short, right? So in that case, even I have a very big N2, but my big L is very small. For graphene, it could be even smaller than wavelength lambda, right? So the corresponding phase accumulation could be nominal. It's never important, right? But is there any solution? You can still take advantage of the big N2 value of graphene, but still with large interaction lengths. Okay. Can you have a win-win situation? So this is the illustrative diagram, schematic diagram of graphene, single layer carbon atoms. But how to increase the interaction length? Okay, this is one smart solution, so-called lab on rod. Okay, so maybe you can hardly tell. 一个像网状的东西，就是它所谓的 graphene. Graphene layer covers the surface of a rod, and the green one is a very thin fiber. Okay, and you know the fiber optics. There is evanescent wave, right? Some electric field will penetrate through out to the surface of the guiding layer. So when light propagates through the green fiber, the evanescent wave will continue interact with the surface graphene of the inner rod, right? So if you round the rod many turns, the interaction distance could be quite large, okay? But how to fabricate something like this? This is one diagram. Do you know PMMA? If you work in the electronics laboratory, it's a pretty common polymer used in electronics devices fabrication. Okay. The green layer means graphene, and the orange one means the copper foil. Okay. Then you have to dissolve copper in some chemical solution, then clean the graphene in DI water. Okay, so it's a process to make single layer graphene, I think. Then you use a rod surfaced by Teflon coating. Then PMMA and the graphene wrapped onto the supporting rod. Okay. So after that, you got something like this. Graphene layer is already deposited over the surface of the rod. Then finally, you round the rod with your fiber. Okay. And after that, you just need to couple the light into the fiber and out of the fiber. You can have light matter. In this case, matter means graphene interaction. And the working distance can be greatly enhanced by this lab-on-rod scheme. So there is always solution as long as there is a strong motivation. Sooner or later, some solution will be found. Okay. Great. Let's go back to cell phase modulation. So let's consider I have a Kerr medium with positive N2. Basically, all the materials have positive N2 coefficient. That means the stronger the light intensity, the bigger the index. Okay. So if I have an input pulse like this, the orange one means light intensity as a function of time. What happens at the output? Okay. First, we think that Kerr effect does not change the temporal intensity. It only changes the refractive index, right? No transmission change. So you can predict that the output light intensity should be intact. It's the same as the input. Okay, so I prime t, I prime means the output intensity, equals I of t, the input intensity. No change about the light intensity. Okay, but phase will change, right? Because the index has been changed. So if we assume the input phase is a constant phase independent of time, what happens at the output? So we have to use the formula we just derived. The index change is equal to minus delta k times L, as I showed you earlier. Okay? And the wave number change is equal to index change n2 times I times wave number in vacuum, k0, right? So anyway, the product is proportional to minus I of t. Okay? So if you have I of t like this, an asymmetric function of time, your phase, output phase, should be also an asymmetric function of time. And with a minus sign, that means the curve is upside down. 好，所以我进来是一个 constant phase， 我出来呢 intensity 没变，但是我的 phase 会 copy 我 intensity 的 shape. If you have a Gaussian intensity, you have a Gaussian phase. If you have a triangular intensity, you have a triangular phase, but upside down because of the minus sign. Okay. So the phase change follows the driving intensity profile itself. That's why this phenomenon is coined by cell phase modulation, SPM effect. Okay. Because the phase change is due to the driving light intensity itself, not by some external source. Okay. And besides, as I mentioned, curve effect is assumed almost instantaneous. So no matter how short your input pulse is, the phase curve will not be distorted. Okay. If your response speed is slower, say response of curve effect is 100 femtosecond, if you drive it with a 10 femtosecond pulse, then the phase curve will be distorted, will be longer than the driving pulse, right? But here we don't have to worry about this because the curve effect is so fast, so there is no distortion about the shape. We can precisely predict the phase modulation in the time domain due to the driving pulse shape. But the next question is, okay, I have some temporal phase modulation, but it's very difficult to figure out what really happens. It's mathematically true, but what does it mean? Okay, so we need some interpretation about cell phase modulation. Let's go back to Fourier transform theory, as we reviewed in lesson 1, instantaneous frequency. In general, after you have some nonlinear temporal phase modulation, you will get a new spectrum. Okay? So mathematically, if small f of t and the big F of omega are Fourier transform pair, then small f of t times a nonlinear phase modulation, e to the j times delta phi of t. Delta phi of t is the temporal phase modulation due to SPM. It's nonlinear, right? Because the shape follows the pulse shape. It's never a simple linear function, right? Then we designate this new function in the time domain as f prime of t. The corresponding spectrum should be some big F prime of omega, which might be totally different from big F of omega, just some new spectrum. It's true, but it's useless. We cannot get any new information by this formula. So how should we interpret just borrowing the Fourier transform property? We know small f of t times e to the j delta omega t, delta omega is some constant. The corresponding spectrum is big F of omega minus delta omega. The spectral shape is the same, but it will be shifted by an amount of delta omega. And the delta omega in the time domain is here. What does this mean? This is a phase function, right? And it's not just a phase function, but linear phase function. Constant delta omega times t. This is a linear function of time. So basically, the frequency shift is equal to the slope of your phase modulation function. 好，斜率代表平移量，好，时间相位的斜率代表频谱上的平移量。It's backed by the Fourier transform property. So if you compare the two formulas, okay, here I have a linear phase modulation, but here I have in general a nonlinear phase modulation. So we should expect the new spectrum should be something like this, a shifted spectrum, but this time the amount of shift could not be a constant because delta phi is not a linear function. Okay? So what is the corresponding shift? It should be the time derivative of your phase modulation function. The way you can get the slope, right, is by first order derivative. Okay, so no matter what is the shape of your SPM, cell phase modulation function, you just take first order derivative, you should be able to get the amount of frequency shift of your spectrum. But remember, now, delta omega is not a constant. It does not just stay there. It could be changed with time. So that's why it's coined as instantaneous frequency. Instantaneous frequency equals the carrier frequency, which is a very large constant, plus the frequency shift with time calculated by first order time derivative of your temporal phase modulation. Okay, so this is something we need to pay attention. The amount of spectral shift now changes with time, and the amount is determined by time derivative of SPM. Okay. So let me show you two examples. The first one is quite easy. If you have a linear phase modulation like the blue dashed curve, what is the corresponding spectrum? Okay. The gray shaded area means the original spectrum without phase modulation. The red time domain function corresponds to the gray shaded spectrum in the frequency domain. After a linear phase modulation, you got a new spectrum, which is a blue solid curve. You see the spectral shape is the same as the gray one, but the center is shifted by an amount of big omega, which is the slope of your linear phase modulation. Okay. In the second example, I assume the temporal phase modulation is a simple quadratic function, sigma over 2 times t squared. Then the time derivative of this one is a linear function, sigma times t. So if sigma is a positive number, what happens? You can imagine without quadratic phase modulation, this is the original spectrum. After quadratic phase modulation, you got a linearly changed instantaneous frequency. The center one is the carrier frequency, but the amount of shift is a linear function of time. So if you have a smaller time, you got a smaller shift, so you have a redder spectrum. If, at a later moment, you have a larger t, you have a bigger amount of shift, then you have a bluer spectrum. So roughly speaking, your spectrum change with time from the red one to the blue side. Okay? If you have a quadratic phase modulation. Before we conclude this part, let me make some remarks about the concept. Strictly speaking, this is not true, because when you talk about frequency, there should be no time, right? According to the Fourier transform theory, you know either a function is in the time domain or in the frequency domain. Either or, right? Function of t or function of omega. When you talk about instantaneous frequency, frequency is a function of time. You see them both, right? 同时出现了时间跟频率两个概念，这严格来说是有问题的。Okay? So usually this concept applies to so-called highly chirped pulse. Your pulse span over a very broad time span, and underneath your electric field fringes change with time. It's called the chirp pulse. Then this concept works pretty well. But if you are talking about transform limited pulse, then this concept is not precise. At that time, you have to go back to the rigorous Fourier transform theory. You have to describe it either in the time domain or in the frequency domain, but not both. 所以我必须做一个补充说明啊，这种瞬时频率的概念是有点模糊地带的。在你的脉冲是所谓的 highly chirped pulse， 它描述的很好，很好用啊，有助于我们了解。我这边介绍它，就是我们使用的这个概念，可以比较容易的去了解到底 cell phase modulation 如何来让我制造出一个更宽的频宽。你必须借助这个概念，会比较容易理解啊。但是这个概念呢，在数学模型上是不够严格的啊。当你遇到了所谓的转换极限脉冲的时候，这样子的概念就会有点失真，就不适合。好，我必须做一个补充说明。